conductors from the transformer to the breaker enclosure are grounded conductors, also known as neutral conductors. These conductors are required to carry the unbalanced current in the system. According to National Electrical Code Section 250.24b2, the grounded conductor must be sized based on the largest ungrounded conductor in any one of the raceways. In a setup with 3 raceways and 350 mcm conductors per phase, the largest ungrounded conductor is 350 mcm. National Electrical Code Section 250.66 specifies that the grounded conductor for service equipment must be at least the ampacity of the largest ungrounded conductor. Since 350 mcm is not a standard American wire gauge size, the minimum size allowed is number 2 American wire gauge. The grounding conductors from the ground rods to the transformer, breaker enclosure, and motor starter panel are equipment grounding conductors. These conductors provide a low impedance path for fault current to flow to the ground. According to National Electrical Code Table 250.122, a 1/0 copper conductor is sufficient for an 800 amp service. Therefore, the grounded conductors from the transformer to the breaker enclosure should be sized as number 2 American wire gauge. The equipment grounding conductors from the ground rods to the equipment should be 1/0 copper. When dealing with parallel conductors in electrical systems, several key factors must be considered to ensure safety and compliance with the National Electrical Code. Firstly, understanding the terminology is crucial. The grounded conductor, often referred to as the neutral, carries the unbalanced load current back to the source, typically a transformer. The equipment grounding conductor, or EG, provides a low impedance path for fault current, protecting equipment and personnel from electrical shock. Grounding electrode conductors connect the equipment grounding system to grounding electrodes, such as ground rods, to establish a connection to the earth. Now let's discuss conductor sizing. The size of the grounded conductor for service equipment is governed by National Electrical Code Section 250.24b. This section stipulates that the grounded conductor must not be smaller than the required grounding electrode conductor specified in Section 250.66. When multiple raceways are used, as in the case of parallel conductors, the grounded conductor is sized based on the largest ungrounded conductor in any one raceway. For example, if you have 3 raceways each containing 350 mcm conductors, you size the grounded conductor based on one 350 mcm conductor. National Electrical Code Section 250.66 provides guidance on sizing the grounding electrode conductor. However, Section 250.24b2 states that the grounded conductor cannot be smaller than 1/0 American wire gauge, regardless of calculations. To determine the appropriate size, you would typically refer to National Electrical Code Table 250.66. This table correlates the size of the ungrounded service entrance conductors or equivalent area for parallel conductors with the minimum size of the grounding electrode conductor. For instance, if the ungrounded conductors are 350 mcm copper, the grounding electrode conductor would need to be at least number 2 American wire gauge copper. However, as previously noted, it cannot be smaller than 1/0 American wire gauge per Section 250.24b2. Next, consider the equipment grounding conductor. National Electrical Code Section 250.122 and Table 250.122 provide the requirements for sizing equipment grounding conductors. The size of the equipment grounding conductor is based on the overcurrent protective device protecting the circuit. For an 800 amp overcurrent device, Table 250.122 specifies a minimum of 1/0 American wire gauge copper. The equipment grounding conductor runs with the circuit conductors and connects to the equipment grounding bus in the panel. Additionally, ground rods play a vital role in the grounding system. Ground rods provide a connection to the earth, helping to stabilize voltage and provide a path for fault current dissipation. The minimum size for a grounding electrode conductor connecting to a ground rod is typically number 6 American wire gauge copper, as per National Electrical Code Section 250.66a. Although you can use a larger conductor, such as 1/0 American wire gauge, the code does not require it for ground rod connections. Now let's address common misconceptions and best practices. It is essential to differentiate between grounded conductors and equipment grounding conductors. The grounded conductor carries neutral current, while the equipment grounding conductor provides a fault current path. Confusing these can lead to improper installations and safety hazards. When installing parallel conductors, ensure that all connections are made properly and that the conductors are adequately supported. Use appropriately sized connectors and ensure that torque specifications are followed. Bonding all metallic components, such as conduit and enclosures, is also crucial to maintain a low impedance ground fault path. Regularly inspect the grounding system to ensure that all connections are tight and free from corrosion. Grounding systems can degrade over time due to environmental factors, so periodic maintenance is essential. Always adhere to local codes and regulations, as they may have additional requirements beyond the National Electrical Code. Local jurisdictions may have specific amendments or interpretations that must be followed. When in doubt, consult with a qualified electrical engineer or inspector to ensure compliance. Keep detailed records of all grounding system installations, including conductor sizes, connection types, and inspection dates. This documentation can be invaluable for troubleshooting and future maintenance. In summary, sizing grounding conductors for parallel conductor systems requires a thorough understanding of the National Electrical Code. Pay close attention to sections 250.24, 250.66, and 250.122, as well as any applicable local codes. By following these guidelines, you can ensure a safe and effective grounding system that protects equipment and personnel from electrical hazards. In electrical engineering, a grounding system is a critical aspect of ensuring safety and proper operation of electrical equipment. It provides a low impedance path for fault currents to return to the source, minimizing the risk of electric shock and equipment damage. The grounding system consists of several components, including grounding electrodes, grounding electrode conductors, and equipment grounding conductors. Grounding electrodes are conductive rods, plates, or other devices that are buried in the earth to establish a connection to ground. Grounding electrode conductors connect the grounding electrodes to the electrical system, while equipment grounding conductors provide a path for fault currents to flow back to the source. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. The NEC is a widely adopted standard in the United States that sets the minimum safety requirements for electrical installations. It covers various aspects of grounding, including conductor sizing, installation methods, and bonding requirements. Understanding and complying with the NEC is essential for ensuring the safety and reliability of electrical systems. One of the key aspects of grounding is conductor sizing. The size of grounding conductors must be adequate to safely carry fault currents without overheating or causing voltage drops. The NEC provides specific guidelines for sizing grounding conductors based on the size of the ungrounded conductors in the circuit. For example, NEC Table 250.122 specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. In general, larger conductors are required for higher current ratings. Another important consideration is the type of grounding conductor. Grounding conductors can be made of copper, aluminum, or other conductive materials. Copper is the most common material due to its high conductivity and corrosion resistance. However, aluminum conductors can be used in certain applications provided they are properly sized and installed. The NEC also specifies the minimum size and type of grounding electrode conductors. The grounding electrode conductor connects the grounding electrodes to the electrical system, typically at the service equipment. The size of the grounding electrode conductor is based on the size of the service entrance conductors. For example, NEC Table 250.66 provides the minimum size of grounding electrode conductors for various service entrance conductor sizes. In addition to conductor sizing, bonding is another critical aspect of grounding. Bonding involves connecting all metallic parts of the electrical system together to create a low impedance path for fault currents. This includes metal conduits, enclosures, equipment frames, and other metallic components. Bonding helps to ensure that all metallic parts are at the same potential, reducing the risk of electric shock. The NEC provides detailed requirements for bonding electrical systems. For example, NEC Section 250.92 requires bonding of service equipment enclosures and raceways. Section 250.96 requires bonding of metal water piping systems. Proper bonding is essential for creating a safe and effective grounding system. Grounding electrodes are another important component of the grounding system. Grounding electrodes provide a connection to the earth, helping to stabilize voltage and provide a path for fault current dissipation. The NEC recognizes several types of grounding electrodes, including ground rods, ground plates, and metal underground water pipes. Ground rods are the most common type of grounding electrode. They are typically made of copper or copper-clad steel and are driven into the ground to a depth of at least 8 feet. Ground plates are metal plates that are buried in the ground to provide a larger contact area with the earth. Metal underground water pipes can also be used as grounding electrodes, provided they meet certain requirements. The NEC specifies the minimum size and installation requirements for grounding electrodes. For example, NEC Section 250.53 requires that ground rods be at least 8 feet long and be driven into the ground to their full length. It also requires that ground rods be spaced at least 6 feet apart. Proper installation of grounding electrodes is essential for ensuring their effectiveness. In addition to grounding electrodes, surge protective devices, or SPDs, are often used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other events that can damage sensitive electronic equipment. SPD diverts surge currents to ground, protecting the equipment from damage. The NEC requires the use of SPD in certain applications, such as in critical care areas of healthcare facilities. It also provides guidelines for selecting and installing SPD. Proper selection and installation of SPD can significantly improve the reliability and safety of electrical systems. Regular inspection and testing of grounding systems are essential for ensuring their continued effectiveness. Grounding systems can degrade over time due to corrosion, loose connections, or other factors. Regular inspections can identify potential problems before they become serious. The NEC recommends regular inspection and testing of grounding systems. For example, NEC Section 250.70 requires that grounding electrode connections be accessible for inspection and testing. Various testing methods can be used to evaluate the effectiveness of grounding systems, including ground resistance testing and continuity testing. Proper maintenance and testing of grounding systems are essential for ensuring their long-term reliability and safety. In summary, grounding is a critical aspect of electrical safety and proper operation of electrical equipment. The NEC provides detailed requirements for grounding electrical systems, including conductor sizing, bonding, and grounding electrodes. Understanding and complying with the NEC is essential for ensuring the safety and reliability of electrical systems. Regular inspection and testing of grounding systems are also important for maintaining their effectiveness over time. By following these guidelines, you can create a safe and effective grounding system that protects people and equipment from electrical hazards.